Alright, I got a fun one for us today. We are going to learn about SIMD assembly. It's going to be great, so let's get right on into it. So we've got, this is our CPU, or something similar enough to our CPU, and we've been focusing on this part. We learned a little bit about this part, and now it's finally time for this other part, the SIMD part, which is called Neon in ARM assembly, which is fun. Alright, so here's a list of every single SIMD assembly instruction. I think I already opened it once. Here, I've just opened it again. You'll see normal things like add and stuff like that, but you're not adding just one register and another into a third. It's like you're doing a bunch of things at once, alright? So we'll get into that, and then if you scroll down, there's like so many that maybe don't make enough sense. Try clicking on some. It's good practice. But yeah, let's explain it from first principles. So yeah, again, Neon is the SIMD part of our processor. It does what's called vector processing, which is the idea of like, I want to run an add instruction, but not on just one thing, on a bunch of things at once. Okay, so let's remember this nice blurry picture that's very helpful for us. Instead of doing this, like one add instruction, add registers A0 and B0 into C0, and then right after it, right, separate from that, add A1 and B1 into C1, separate from that, same with the 2s, same with A3, B3 into C3. Instead of doing 4 separate instructions, what SIMD is all about is we are going to chunk together, we're going to do one add instruction on all of these things at once. It's like add A0 and B0 into C0, A1 and B1 into C1. Just one big instruction that does all of that for us, okay? So, yeah, you can do this kind of thing, and here are the kinds of data types that support these SIMD operations. You can do, you can act on multiple things at once. So you can do SIMD stuff with floats, a bunch of floats, a bunch of doubles, a bunch of whole numbers, a bunch of integers of varying sizes, 8, 16, 32, 64-bit. They can be signed or unsigned, doesn't matter. So that's pretty nice. And then there's one thing called Boolean polynomials that this stuff also works on, and I do not know anything about this. I did not read enough about it. So maybe you can teach me, but we're not going to focus on that bit in this class. Okay? But yeah, here are the registers that you get, similar to, like I was saying in the floating point assembly lecture. You got a bunch of them, and you see some pieces that you kind of know about already, maybe. So you get 32 128-bit wide registers, and they're called V0 through V31, which kind of stands for vector, right? So you don't have to just store a single 128-bit number in each of them. You can chunk them up, and that's the goal, all right? You can put a bunch of little things inside. So like here's a picture of all your registers. Here's like V0 and all the different ways you could chunk things up inside of it, all the way ... to V31, and you can do however you need to do it, all right? So it would appear that my PowerPoint is unhappy right now. There must be a bug in PowerPoint. That's no fun. So I am unable to do Control-Z at the moment, and it is frozen. So I'm not quite sure the best way to go forward from here. I might just have to like quit it and come back. It's a little scary, but it seems to have done what it needed to do. All right, well, let's keep on trucking. Maybe if I tell it to not save, let's see if that helps. So okay. Yeah, here's what you can do with all of your registers. You can put not just a single number. You can put 2 doubles. You can store 2 doubles per 128-bit register. You see how you can kind of chunk those in. See how that's working? V0 dot, treat it like 2 doubles. Or if I zoom in here, that might help. This is just V0 right now. You have 32 of these guys, but you could also store 4 floats, single floating point numbers, or like these could be 64-bit ints as well as 32-bit ints. Doesn't matter, but you can put 4 floats, 4 single floating point numbers, or 4 integers, 4s, word size things. You could store 8 16-bit numbers, which are like H for half words. Treat V0 as holding 8 half words. Or you can split up on the byte level. You can treat V0 as holding 16 different bytes, couldn't you? That's pretty cool. You can treat it like any of those, and these can be floats, doubles, or like 64-bit whole numbers, or ints. So maybe I should change that. Ints, doubles, or like longs. That's 64 bits, right? So that's a thing. Cool. You have these options now. All right, so let's talk about how to fill them now. Let's talk about how to fill these registers like V0, V1, V2 in a different way, because you gotta get stuff in here, right? And they gotta be chunked. So how do we do that? How do you load and store data into these V registers? All right, 128 bits for stuff. How do we do it? So if your data is contiguous in memory, like here's a picture of memory, here's some data, contiguous land, you can first of all, you can fill up the entire register, or you can fill up the first half of the register, right? You can treat it as holding like only 8 bytes, and we're not going to use the upper bits. Only do the lower 64 bits, or you can treat it as the full 128. Okay, you have options, but yeah, that's the idea there. If you want to load and store contiguous data, hopefully this pretty picture that I worked hard on will help. You're going to use LD1 and ST1, all right? And so look at the documentation for these. These are weird to wrap your mind around. So like we're going to LD1 this thing, all right, into a single structure. So there's a bunch of different ways to use it. I will do my best to explain, but the documentation does help if you read it long enough, okay? So, okay, the one means your data is contiguous. I'll talk about what it means to have not contiguous data in a second. And so you're going to say LD1, and then you're going to put one or more registers that you want to read into. You can read into more than just 128 bits at once, but we're just going to deal with reading into a single V register, all right? And the registers you want to read into go between some braces, so it's a weirder kind of instruction, and then you give an address where something starts. So here's the idea. Let's say I have 16-bit data. Here's 16-bit data taking up addresses 24 and 25 for this red thing. That's 16-bit data. And then 26 and 27 take up this orange thing, 28 and 29 make up the yellow. And so I've got 1, 2, 3, 4, 5, 6, 7, 8 16-bit things. And what I'd like to do is put them in a V register. Do you see that it can hold 8 16-bit things? Woohoo! So that's nice. So yeah, I would like to read 8 half words into all of V1. So I'm going to say v1.8h. All right, load 1 v1.8h between curly braces. All right, and starting at the address held in a normal ARM register at x1. Okay, that will shove these things into V1 and interleave them in this way. All right, or not interleave them. They will be contiguously stored. They'll be chunked up in this way. And like the red part is like the highest bits of the V register. The orange part is the next highest 16 bits. But that's how you get it all into a V register, and it kind of looks like this one. Does that make sense? So that is the trick. With more examples, it'll make more sense, I hope. So that's how you do loading and also storing. You can store back to memory in the same way. There's a store one, okay, just like there's a load one. So yeah, you can give up to 4 V registers to load into at once. Like you can store like a bunch of stuff. Load, like starting at x1, like read so many things that you've run out of room in V1 and then put the rest into V2. That's pretty cool, isn't it? So that's a thing that you can do. You can give up to 4 V registers to load into all at once. So that's like happening in a clock cycle. It's one instruction. It's weird to think about. So that's how you load and store contiguous data, all right? Your data might not be contiguous, though. You might care about an interleaving to your data, all right? So it might be the case that, like, your data is chunked up. You got a red and orange thing, and they're kind of like 2 different ideas. Like this is thing 1. I don't know how to think of it. Like this is, like these are pieces, right? Let's say that your data is chunked up like this. Red and orange, then yellow and green, then blue and purple. Like these 2 together mean something. And this is like part A, this is part B. And this is part A, and this is part B of the second thing. This is part A, and this is part B of the third thing. Okay? Pretend that that is true. And you care about, like, I want just the A's right now, or I want just the B's right now. And get them together. Do you see how it's interleaved? Okay, that's the idea. So you can use LD2, 3, and 4 for interleaved data. And then store works the same way. Okay? They each need the same amount of registers. So LD2 needs 2 registers, LD3 needs 3 registers, LD4 needs 4 registers. But here's this example. Let's say I want to get all the A pieces together. So I want the red thing, I want the yellow thing, I want the blue thing, then I want the green thing, or sorry, gray thing. That idea. You see that? and then do it all over again for the rest. I would like that just in V1, just the A parts in V1, okay? Just the A bits, dot, dot, dot. And I want just the B bits in V2. See how that might be useful for you one day? To do that, it's an LD2 because it's interleaved, like it's switching over every two, okay? That's the idea. So the way that this works is you give two registers. I want to say LD2, my stuff is interleaved every two things, every two 8-half words. So I want to load into, within curly braces again, the first stuff, the first interleaved stuff by 2, I want to load into V1, and I would like to fill 16 bits. Take 16 bits at a time, so like the A thing is 16 bits. Sorry, it's 2 bytes, okay? 24 addresses 24 and 25, that's the first thing, then 28 and 29, because we're offsetting by 2. So read all those A parts into V1. They're separated by half words. There's 16 bits, and I want you to read all 8 of them, as many as you can fill. Okay, that's kind of how you read that. And then you say V2, I would like you to take, please, the other side. I want you to read in half words, so 16-bit things, fill in your entire self, so you can hold up to 8, put all 8 in there, and that's how you talk about it. And we're starting at address x1. So like these chunked things all together, they mean something. You have A parts and B parts, and we want just the A parts in V1, just the B parts in V2. All right. Hopefully, it's hard to hopefully you can kind of understand why that would be useful, and yeah, you can kind of see it from the picture. The picture is better than my explanation, that's for sure. Okay, so with that, can load and store. A very, very good example of why you would want to use interleave data and get a bunch of things, like the first bit's over here, the second bit's over here, is with images. So images are arranged in this way, right? You have RGB colors, and I'll talk about that if you're not too familiar with it. An RGB color, for example, is represented by 3 bytes, 3 8-bit values, and the first byte means how much red was in the color, the second byte means how much green was in the color, the third byte means how much blue is in the color, and then that's it. That's your first color, then your next color in your image comes after that in the next 3 bytes, then your next color goes in the next 3 bytes. Can you imagine that you might one day want to get all the reds in one register, all the greens, and all the blues in different registers? Okay, so that's an interleaving. All right, so an image is an array of RGB colors, one for each pixel in the image. Let's pretend that x3 points to the start, right, of this stuff. This is pixel 1, red, green, and blue, pixel 2, red, green, and blue, etc. I'd like to read them in like this into V3, V4, and V5. So I want the 1s here, the 2s here, so on and so forth. All right, so my image is chunked, just like this: red, green, blue, red, green, blue, red, green, blue, all day long. Okay, so I'd like to fill in all of V3, V4, and V5. So I'm going to read in how many bytes. So that's 16, 32, 48, I guess, 48 bytes total. So you're taking a while. You're reading in as much as the V registers can possibly hold, and it's interleaved. So which LD instruction will you use if X3 is holding your pointer and you want to read into V3, V4, and V5? All right, so here's that example again from the previous slide. See if you can use this idea, and then also this picture with the dots, right? Those are important. Which dots do you need here? Doubles, singles, half words, bytes, dot, dot, dot. You want to be looking at that picture as well as this example. So, can you figure it out? All right, hopefully you found it. It's going to be LD interleaved by 3, like the red is every 3 offsets away. Does that make sense? It's chunks of 3 things. It's going to be LD3, and then what we're going to say is, all right, I want to read into, if we follow this pattern again, I want to read into not V1 and V2, but V3, V4, V5. So V3's got to have something, V4's got to have something. I'm leaving space for myself, and then V5's got to have something. And then I need the dots to describe what kind of stuff I want. And then I want to read into it from the address in X3. That's my starting address. All right. And then I need these dots. Dot something goes here. All right. So what's that something? It's not, I want to fill in 8 half words. I want to fill in 16 bytes of things. That's the interleaving. That's the granularity of everything. Okay, that's how that's going to work. So it's going to be dot 16b. 16b for all these bad boys. Okay, just like it's saying here. Go back to that picture when it gets confusing. Did I give myself enough room? We will find out. So that's supposed to be a B. It does not look like a B, does it? V5, treat it as a bunch of byte values, 16 of them in total, to fill up the V registers. So do you see that this is the instruction, this is the answer, that's going to fill in V3, V4, V5 from the starting address. Okay, that's how you do it, and I hope that makes a little bit of sense. All right, so yeah, it just takes practice to wrap your mind around it, but it's very cool to think about, that's for sure. All right, so now let's actually do stuff. All right, we've got stuff in our registers. Let's like do an addition. Let's take V1. Let's say that V1 holds these numbers, V2 holds these numbers, and then I want to add them up, each chunk of them, into the corresponding parts of V0. So like the 1 and the 2, bring them together. This guy and this guy, bring them together, add them, and then shove the answer in this part of V0. All right, and then do the same for all of them. We're gonna chop them up just like this, and do the operations and put the answer in the corresponding part of V0. Okay, so here's kind of what your operations are going to look like. You're going to say your operations name, and then you're going to talk about which register like is your destination register and what kind of how it's chunked up, what kind of stuff is there, and they're going to do the same for your operand register. So like VN and VM is where you're doing your operation from, like you're taking the data from there, and then how are they split up? What kind of chunking is going on there? And they should all be the same. This red thing should be the same every time. All right, so your operation, usually, there are certain ones where it's different, but usually for now at least. All right, so your operation can be all the stuff kind of that you know and love. There's add, sub, multiply, shift left, shift right, absolute value, a lot of things. Go back to the page if you want to know more. They all can take these kinds of vector registers, and your type can be any of these ones from this picture. So you can talk about the entire 128-bit vector, so you can hold 2 doubles, 4 singles, 8 half words, 16 bytes, or you could just talk about the right half of your V register. So you could hold a single double, two 32-bit values, 4 16-bit values, or just 8 bytes. Either way works. All right, but usually you want to fill it up unless you have a good reason not to. So yeah, let's use let's see. Yeah, these smaller numbers use the right half of the register only. So instead of like 16-bit bytes values, you could have 8-byte values. Instead of 8 half words that fills the whole V register, you can just fill half of the V register with only 4 16-bit values. So summing to 64 bits always. So same with these guys. And then you can do 2D or 1D. And I guess I forgot to say that one. Dun, dun, dun. 1D. 1D or 2D, and I ran out of room, darn. There we go. Okay, so yeah. So let's pretend that we've got, let's see, these registers set up, V1, V2, they hold, they're filled up holding 8 different values, and let's say that that is the entire register, and these are 16-bit values, all right? You have 8 16-bit values here, 8 half words, 8 16-bit values here, and we want to shove them into the corresponding parts of V0. I want to add them up, all right? So yeah, go back to the instructions link for more, but here's how you would use this kind of idea, all right? I would like to add, please, from V1 and V2, split up as having 8 half words. So look at 8 chunks of things, 8 half words. Take those guys, all right, that's key. So that's going to be propagated everywhere, and then I'd like you to add them up and put the answers into V0. All right, that's what's going on. That's how I want to do it, and it's going to be add on just normal whole numbers. Okay, V0 into V0, chunked by 8 half words. All right, and this is going to give us integer arithmetic. Dun, dun, dun. You might be wondering, like, what if there were floats there, or like if I was using 32-bit values or something. The way that you get floats, dun, 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 is it's not add. I think it's going to just be fadd. Dun, dun, dun. You can do a floating point vector addition. and then it knows like, oh yeah, if you say 4S or whatever, then it was like 32-bit floats. So that's kind of how you do it, but that's beyond the point right now. All right, so this is, hopefully you can see how this instruction corresponds to this kind of operation where you're taking these pieces and bringing them into the third vector register. Okay, so yeah, I think that is a good introduction. I now want to give you an application. So we're going to do image processing because this is a cool idea, right? This is one of the hardest lectures, but it's also going to be one of the coolest lectures in terms of what we will produce. We are going to mess with images. In particular, we're going to mess with bitmap images, .bmp images, which is an older format, but it's easier to like pick apart and mess with. All right, so every image, first of all, if we're not very familiar with this idea of RGB and colors and things, most images are stored in RGB color format, and here is kind of how that works. Every color in your image is 24 bits long, so it's 3 bytes total, and the first 8 bits are how much red are in that pixel, the next 8 bits are how much green, and the last byte is how much blue. And so I'll kind of like write colors as it's a triple of things, right? It's how much red, how much green, how much blue, and you can have 0 to 255, the smallest amount to the largest amount, because it's a byte value, all right? So like bright green, for example, would be no red, all the possible green, and then no blue. That would give you bright green, okay? And I think you can imagine like red would be 255, 0, 0, okay? RGB as a color system is weird. It's not like paint. It's like light. It's additive. So the max color, 255, 255, 255, all the red, all the green, all the blue, combined together to make white. Okay, it's not like a bunch of paints mixed up and it like turns into some muddy black. All right, none of the colors. 0, 0, 0 means black in RGB. All right. And you can kind of extrapolate, like these values are equal to one another, and now you've got like a perfectly neutral color, white or black. It is true that when the red part is equal to the green part is equal to the blue part, you get a perfectly neutral shade of gray. So that's kind of useful. It's like 112, 112, 112 is some shade of gray, some mid-range shade of gray. Okay, perfectly neutral, not hot, not warm, not cool, perfectly neutral. It's beautiful. All right, so that's how you can think of that. We'll come back to that in a second. And then we have the bitmap file format. So this is one way to store images, all right, in the bitmap file format. And I have some starter images that I've populated. I've got a picture of my cat, and I got some pictures of our campus that we're going to mess with today. But the bitmap file format is an interesting one. If you go to the Wikipedia page, you can read about it. It's kind of how I learned how to break it down. But it starts off with this header part. When you go into the file, it's like, and it tells you eventually like how wide the image is, how tall the image is, and then eventually, if you scroll down enough, it's like it talks about how like colors are stored, etc., etc., where the pieces are in the header, and then eventually you have like an array of colors, an array of all the image data after you like the starter header has told you like how wide the image is, how tall it is, and all that. Then you have the actual colors themselves. Okay, so read this if you're interested, and I've made you some code that will get us started here. But take my word for it that pixels start and are stored in the bitmap image format like this, which is kind of counterintuitive. This is the way the image is arranged in memory. So once you get to the array of pixels, they're going from, they start in the bottom left. The array like starts off in the bottom left. It goes left to right, bottom to top. Bottom to top. So like this is the first pixel in the array. The first thing in the array corresponds to this pixel way down in the bottom left. Then this one, then this one, then this one, then this one, all the way to the right here, and then it jumps up, and like the next pieces of the array of colors are talking about the next second to last like line of pixels, then the third to last line of pixels in that order. So then you make your way up, and that's how the pixels are arranged in a bitmap file for some weird reason. And then, sadly, the colors, yes, they are stored in RGB format, but they're kind of backwards, all right? So it's not red, green, blue. They're not going to be stored like this, surprisingly. It's weird to think about, I know, but in bitmap file format, they are stored in BGR format. They're stored in backwards RGB format, which I know is disgusting, and we will have to remember that as we're loading stuff. So like this is not what's happening. It's going to be blue, then green, then red a bunch of times for bitmap images. I'm so sad about that. And then also another weird thing to have to worry about is that every row of pixels, like after this pixel, it doesn't immediately come this pixel usually. There is usually some padding for alignment purposes. The next row is always going to start at a multiple of 4 bytes into the image file, okay? Because again, aligned memory is very easy to read. It's faster that way. So I've took care of that. Don't worry, I'm going to give you a lab on this eventually. This is why we're going into it. And I'll give you examples of messing with images. But I will take care of all of this idea for you. Don't worry, I'll just give you an array of pixels and it's in this format and you'll have to deal with it. But everything else, like the padding, the read align, and like work your way upwards, I will take care of for you, okay? So our goal, is to use vector operations, because they're fast, to edit all the pixels in an image to do something cool with them, all right? So that's the goal. That's what we're going to do for the rest of this lecture, and I have some fun examples for us, all right? So here's actually another picture, though, of the kinds of ways that you can access your V registers. So this might be another one to look into. So like you can treat it like 2 doubles, 4 singles, so 4 32-bit values, 8 16-bit values, 16 single byte values, or 8-bit values. Or you can just look at the right half, right? You can just treat the right half as like a single, double, 2 32-bit values, a single 64-bit value. I shouldn't be saying double because it could have been a whole number, all right? 2 32-bit values, 4 16-bit values, or 8 8-bit values, all right? 8-byte values. So with that, that might be helpful for you. So yeah, load 3 into a bunch of vector registers, reading 16 bytes at a time, right? Because it's 1 byte per color. That's our best friend right now, okay? So I'm going to steal some boilerplate code from a future lab, and I can't quite remember which one it is, but we're going to bring it in here, okay? So copy standard code 45. I forget which lab we're even on right now, so let me look at a few of these. It's not that one. It is not that one. It's not that one. It'll be this one. All right, so eventually, lab number 8 is when this is going to happen. So I will copy. Dun, dun, dun. I've already got the files that I care about, at least most of them. I've got the image files that I care about in the directory already. I just need to bring in, which one do I want to bring in? I don't know. I guess I need, well, first of all, I need the make file. Bring that here. I'm gonna need probably darken, honestly. I'll bring that in here, and then definitely filter.cpp. Oops. I think that's enough. I think that's enough for now. And here's what we're gonna do. All right. This is the part. This is your lab. I'll show it to you later. But what are we gonna do? We're gonna make some examples called like swap. I think I want to do that. We're gonna swap some color channels, and so I'll rename darken to be swap colors.s. That's better. And then filter.cpp is going to deal with that. So here's kind of the idea. I've got filter.cpp that is a CPP file that reads an image. It takes an image file as part of like command line arguments, and it takes an output file. We'll change these in just a second. This is from your lab right now. And it reads the file in binary format, and it parses the bitmap image, and it gets the actual like pieces of it. And I have this is how you can find the image width and height and the starting address of the colors and all that, the array of pixels. And so I take care to make sure like everything is padded properly. You can read this file if you're interested, but we're just gonna use it. All right, it's making sure that you can never go too far, even if you use even if the last bit of the pixels on a row was like a little less than 16 bytes, it'll still be okay. It's taking care of all that for you. And then it's calling one of our filtering functions, okay? And it's like cleaning up after itself. So that's filter.cpp. It's going to run what we're about to write in assembly, okay? That's the goal. So yeah, what we're going to do is we're going to make two functions. We're going to make swap colors simd, or sorry, simd, and we're going to make bw simd, all right? And that is going to repeatedly like mess with pixels. So it's going to be dun, 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 swap colors simd and bw simd. All right. And so these are the functions that we're going to write in assembly. We're going to get an array of characters. It's an array of bytes, right? For the pixels, for the current row of pixels we want to act on, and we're given how many there are. This will always be a multiple of 16 because I've made it nice for us. This is not always true though. And then same for this one. This is going to like mess with the colors, swap them around, the reds, the greens, the blues, and then this will convert our image to black and white. So we're just going to mess with these pixels using our simd operations, okay? And so I guess let's mess with this filter file so that we can call these functions instead of like having stuff from your lab as possibilities. We want like swap as a possibility or like bw as a possibility. All right, so that's how we're going to use it. Boop. And then once we figure out which one we were asked to do, so if it was like swap, we got to do our swap colors simd versus bw simd. Okay, and that should do it. That's all I think we need for this file. And then so I'll call my assembly files, get back to here, I'll call my assembly files swapcolors.s, and then I'll also make a one called swapcolors.s, and then I'll make one called bw.s. So now they're both available. Go back to my editor. All right. So let's just get the boilerplate for this started. We've got this is going to be bw simd. That's that one. And then this one is going to be swap colors simd. So this is just stuff I got to do to get us started. Just stealing stuff from the lab. And then, yeah, this is its colors. Dun dun dun. We'll talk about how to do it in a second. I'll change these comments that were from the lab. But that is at least this first line is correct. All right, so I think we're good now. All right, so here's our goal. We're going to make these two functions, and we're going to repeatedly, I think I need to change these. We're going to put the next group of pixels not into these. Sorry, this is last semester stuff. We're going to put the next bit of pixels into these registers, V0, V1, and V2. Remember that it's going to be in that horrible BGR format rather than RGB. We're going to mess with them. We're either going to swap them around, swap the reds and the greens or something, and then we're also going to, in a different version, we're going to make our image and convert it to black and white only, which is cool. So that'll be fun. And then, so after we mess with the pixels in our V registers, we have to store them back into where we got them from, because each time we're going to have we just got an array of pixels. We read from them into V registers, we mess with them in V registers, we have to write them back to memory, because that's going to eventually make its way to a file, okay? So, yeah. If you were doing this without my help, you'd have to worry about, like, when I hit the end of this row, maybe there's only like 7 pixels left rather than 16 to read, so like I can't read too much, otherwise I'd like bleed into the old row or something, or into the next row, and that will mess things up. So you'd have to normally worry about that, but my code is watched for that, and it makes sure that like everything is fine, okay? So yeah, every time your function is getting called by my code, it's working on a new row of pixels, and it's your job to just mess with them now, okay? It's our job in this example. Okay, so let's make our first example the easier one. Let's swap the color channels, well, like the red and the green or something, okay? That's what we'll do. So let's swap red and green And so let's think about how we're going to do this, and try to pause the video the second you like think you can do it, and try it. I think it'll be very good help and practice. So let's swap red and green. So somebody's calling, first of all, somebody's calling us like this. They're saying swap colors, SIMD with some pixels in X0, right? And then like the size, the number of, I think, pixels, right? The number of pixels you need to process in this line, in this column of the image. So something like that, okay? So this is going to go in W1. That's like the number of pixels you need to mess with. It's always going to be some multiple of 16. Maybe it's like 32 or something. I don't know. Something like that. And we're going to swap red and green. So we're going to, like, here's what memory looks like once you go to the place in X0. It's a bunch of pixels stored in the disgusting backwards format. So it's going to be B, the first thing is the blue bit of the first pixel, green of the first pixel, red of the first pixel. Then that's the end of the first pixel. Then it goes BGR again for the second pixel. Then for the third pixel, or I guess there's only two, but you get the idea. BGR, if there are more, it would work like this, yeah? So that's what it looks like in the array, and you're going to read just so many. And we're going to swap red and green. So every time we see red, like, for example, we're just going to swap the channels of them. So like, just swap the red and green parts. So if we saw pure red, we're going to transform it into pure green. All right, 0, 255, 0. I hope that makes sense. Okay, that's the goal. And I'm still writing this in terms of RGB because that's normal. This is backwards. We'll have to remember that though. Okay, so you give this a try. Let me fix the comments at least. We're doing swap colors this time. So we would like to swap, right? To swap the colors. We want to implement this to swap the colors of num pixels, starting at pixel start. That's our first thing, okay? What we're going to do, right, is our game plan that we already figured out. And here is, this is still true. Okay, this is still true right here. Num pixels is in fact guaranteed to be a multiple of 16, so you can always use your 128-bit V registers. Like, fill them all up, okay? That's the goal. So I think we're good to go. Now we have something in X0, that's the start of our pixels. We know how many there are in W1, okay? And so what we would like to do is just loop, yeah? We're going to loop and keep on reading a bunch of pixels, 16 pixels, and messing with them, all right? So we're going to loop, and we'll just use num pixels, we'll use W1, we'll just keep on making it smaller and smaller by 16 every time, because we're going to be processing 16 pixels at once, because that's how many can fill 3 different V registers, yeah? So that's our goal. So let's compare W1, that's our number of pixels left, to 0. That's how it'll work. We'll keep subtracting from num pixels, which is what's in W1, every time we process more. All right, that's how that'll work. And then, yeah, if it's like equal to 0, or if we mess up, LE is probably a good one. Hopefully we'll never mess up though. Less than or equal to 0, then we are definitely done. There's no more pixels left, that's for sure. Okay, so this, if we were good programmers and we were confident that this would always end up at 0, and we kind of are, we could do BEQ, but I'll just do BLE just to be safe. Fewer seg faults that way, just in case. The image might look weird though if we mess up. So now our goal, right, is we have a bunch of pixels right now. We have a bunch of pixels. X0 is pointing to the start of them. Let's read them. So read a chunk of pixels, all right? Read a chunk of pixels, process them in the way that we just talked about, and then we got to write them back. Write them back to memory, and then we just read, we worked on 16 pixels from, like, they were in X0. We'll just advance X0 to give us a new chunk of pixels. That'll be good. So advance X0, and then that means we just processed 16 pixels, subtract that many from pixels start. All right, so that's kind of going to be our loop. All right, I hope that makes a little bit of sense. So yeah, let's read a chunk of pixels, and again, the second you feel like you can do some, stop the program, or stop the video, pause it, and you try. It's really good practice, all right? And then see if what I did was what you would do. So we're gonna do this, okay? So let's load 3 into my V registers. Interleave by 3 things. We're gonna load into V0 a bunch of like 16 bytes of that's gonna be the blues in V0, yeah. Then the greens in V1 and the reds in V2. And the address where those pixels start is X0, okay? Because that is our first argument. All right. Now our goal is to process them. We're gonna swap, right? Swap red and green. Honestly, there's no real need to swap anything right now because you can just write them back in a weird order and it would be fine. But let's just be fun. Let's swap the values that are in it's BGR, right? So V1 and V2. Let's swap their values. Why not? All right. So let's use V3 as our temporary thing. So there's a move, right? There's a move operation on our V registers. So move into V3. For some weird reason, you still have to do it this way with the .16b. Move those 16 bytes from V1, chunked up like that, into V3, and then we can like move over V2 into V1 because we've saved V1 now. So V2 we can move over all its 16 byte chunks of things, all its different pieces of those pixels, and then we'll do this. We'll move back into V2 the stuff that we saved safely away in V3. So that's you see that'll swap the values in V1 and V2 using V3 as our temporary register, and now we can just write them back, right? So the corresponding load is a store, and we're going to go back to the same place in memory. Those existing pixels, store them right back. Kind of in the same way now, because I could just keep the same V1 and V2 in that order now. If I didn't want to do this, I could have just done like V2 then V1. It would have worked. But this is cool. You can see like the correspondence between the load and the store. So load the blues back, load the greens back, load the reds back, and we've messed with the reds and the greens. So that's pretty fun. Okay, so that's nice. And then we want to advance X0 because like we don't want to work on the same pixels again. We want to work on 16 pixels later, right? Because we just processed 16 of them. And so how many bytes do we need to offset X0 by is now the question. Like how many bytes, what's the next address at the start of the next chunk of pixels that I need to work on in the next round of my loop? It's going to be 16 times 3, right? 3 bytes per pixel, plus we just messed with 16 pixels. So let's think about that. Let's break it down. So V0, V1, and V2 are all 128 bits. That's 16 bytes. So how many bytes did we just mess with? So we're reading 48 bytes total. That's 16 times 3. Okay? That means the next address that we want to mess with to read from, that'll be the start of the new chunk of pixels we want to deal with. That is 48 bytes from now. All right, and so it was X0. That was always the start of the pixels I want to mess with right now. So I'm going to advance X0 by 48 bytes. All right, so add X0, X0, 48. I hope that makes sense. All right, and then same, we want to know that we're at the end of the loop when it's W1. That's our number of pixels argument. So just keep on subtracting 16 from that. All right, so sub W1 16, and then we just go back to the start of the loop, BL loop, until we're done. All right, and done. I need to make a done label, of course. So this can be done right here, and that should do it. That should do it just like that. Okay, that's my swap color SIMD function, and we can watch it work. We can in fact watch it work right now. Let me mess with the makefile, I think, because it's got to be yeah, it's not gray and darken anymore. It's going to be bw.o and swap colors.o. So let's see if that works. Cool. And so now I'll do this. I'll say /filter, and it expects the following. We say /filter, you give the operation swap is the one we just implemented, and we can give some, like we can give a an image as input. Dun, dun, dun. So I'll do my cat, of course, lonzo.bmp, and we give a name for our output image. So I'll call it lonzo.maybe-swapped.bmp. And it's going to run our stuff. You see it worked in the blink of an eye because we were using very, very fast operations, right? These are vector operations. They're working on a lot of the image at once, and so very quickly did it make that new file, in theory. There it is. And now we just like to view it, and I guess the easiest way to view it would be for me to push this code right now. So let me do that for us. Dun, dun, dun. Oh, let me make sure that I didn't mess up. Okay, I think it's happy. So cool. And then we'll go to here, and it's going to be F24, code from class. 45. And there's our stuff. And then, so here is the original picture of my cat, and here's the swapped one. I gotta click this button now. So, moment of truth, let's see if it actually worked. So here's the original picture of my cat as a kitten. And he is, let's go back to the code for a second. Yeah. So he's laying on my running clothes at my old apartment. So here he is, and what we did is we swapped red and green, right? So here is a very red looking running shirt. In theory, it should be a green shirt, and it is now. Good. Okay? Because Alonzo is a great cat, he mostly stayed the same, which is fun to think about. But yeah, that's what we just did. We swapped those channels, and now we've got an interesting result. Isn't that fun? So yeah, that's the beauty of this. And we worked on this image very quickly, very, very quickly, because of like these vector operations, 16 pixels at once. That is pretty darn fast. Okay, so that's great. All right, next problem for us. Let me show you my next example. This is going to be a more involved one. We're going to convert our image to black and white. All right, this is going to look a little funny. It'll be fancy. I promise it's worth it. So what we're going to do, all right, sorry if you see me make a mistake through the screen, but we're going to only read 8 pixels at once this time. Instead of v-loading, where am I? Instead of loading into v0.16b, v1.16b, v2.16b, we're going to do 8b instead, all right, for a very good reason. We finally have a good reason for it. Back to this image. So we have that opportunity. We can just say 8b, only read in to the rightmost part of that vector, all right, of that v register, even though I know it has more room. 8 pixels at once, all right? We can only process 8 pixels at once with the way that I want to do this, all right? So 8 pixels at once only into the right half of our v registers, all right? And what we're going to do is we need to compute one way to make a black and white, first of all. One way to, like, sorry, I should say this first, shouldn't I have? What we're going to do is we're going to average the pixels, all right? And that's going to tell us how bright it was, because you can kind of see that, like, white is, like, that's the biggest value for RGB. Black is the smallest value for RGB. If I want to convert my image to black or white, I got to pick, like, do I shove this pixel up to be white, or do I shove this pixel down to be black? And you can kind of get at, like, how bright the pixel is by taking the average of its RGB values. If it's a large number, close to 255, it's white. If it's a small number, close to 0, it should be shoved down to be black. And that's kind of how you can do a thresholding operation. So, like, if we have an image that's kind of light, like this, we should make it pure white, all right? Or if we have a pixel that's close to being dark, whatever color it really is, let's shove that and make it black. Does that make sense? And a way to figure out how bright our pixel is and whether or not we should make it white or black is to take the average of the RGB values. So we're going to compute R plus G plus B over 3. All right, that is our goal. And this is why we can only do 8 pixels at once. Because the first thing we have to do, because we're going to add up R, G, and B values, do you know, or can you tell, like, if those values were all 255s, if it was white, we would have overflowed. We would have overflowed our 8-bit values, right? Because 255 is as big as it gets. So the very first thing we need to do is extend, UXTL. extend and elongate our V register, this part of our V register, into another V register, instead of as 8-bit values, as 16-bit values. Do you kind of see what needs to happen here? That's what we need to do. Make everything bigger, double the size, because then we could add them up and we won't overflow. All right? That's where we're going with that. I hope you can see it. So things that were small became large. 8 bits becomes 16 bits. All right? That's what we're doing. This is not to scale, but now we can't overflow when we're doing this calculation. That's what we needed. Okay, that's why you can only act on 8 bits at once. 8 bytes at once. 8 pixels at once. Okay, so we'll add up all of our RGB values, and we have the sum, right? And then we have to divide by 3. All right. Or an alternative, because it's hard to do division in vector land, is let's just have a threshold value of like the middle of the row. Like what is like 128 is halfway between 0 and 255, right? So let's just check like if the sum is bigger than 384. If so, it's like it's white enough, we'll make it white. If it's smaller than that, we'll make it black because it's closer to 0, 0, 0, 0, rather than 255, 255, 255. Okay, so that's what we'll do. We're going to move a threshold value into every part of a register with a move I instruction. It's going to be move an immediate value into each chunk of a V register. And we're going to do 8 half words. So this is kind of how that works, not to scale. So we're going to place an immediate value into each piece so that we can compare against each part. All right, I promise this will make sense once I do it. And then we're going to compare our threshold value that's been duplicated a bunch of times with our summed RGB values per 8 pixels, and then it's a CMGE one. We're going to compare for greater than or equal to. So it takes our V registers, each chunk of them, like this chunk and this chunk, it'll compare it for greater than or equal to. So it'll do greater than or equal to here, greater than or equal to on that one, greater than or equal to a bunch of times, and it will put a bunch of ones, all ones, in this register if it's true, or all zeros if it was false, if this was not greater than or equal to this. Okay, it's very weird how that works. It's not like true or false. It's going to set this register, that chunk of the register, to all ones if it's true, or all zeros if it's false, in binary format, or all zeros. Okay, and that's really nice because for us that's white and black, because white is all ones, black is all zeros, 255 versus 0. And then we have these big 16-bit things still. We need to make them pixel sized, and so we want to reverse extend and narrow down our registers. So we had these big things, we need to make them small again. So big things need to get smaller. So take our 16-bit values, make them 8 bits again. So this image is not to scale again, but you can kind of imagine that's what's going to happen. We're going to narrow rather than, we had to elongate to make it work. Now we have to narrow back down to have pixel-sized things. All right, and then our result is some number. It's either 255s a bunch of times or zeros a bunch of times. And because our value is going to be black or white, that's just a bunch of either 255s or a bunch of zeros. We can just store back whatever we get back from our comparison and narrowing it back down into every single channel, the red, the green, and the blue, because it's just duplicated a bunch of times, whatever it was. Okay, I know that was a lot of words. It's hard to explain it, even with these images. Okay, it's a very fancy process, but I hope that you can kind of see what's going on, and the code's going to make it make sense. Okay, so let's take this. We can steal most of what we have here into the other file. Let's go to bw.s. Let's see. I kind of want to steal everything that we just did here. So a lot of this is going to be very similar. Let's see how much we can get away with stealing. Something like that. But still, it's a bit different. So, all right, let's go to code, and this should hopefully make sense once we hit the code. So here is our function. It is going to convert num pixels starting at pixels start to black and white. Again, num pixels is guaranteed to be a multiple of 16, even though we don't even need that for this one. We just want to use 8. We're going to read 8 pixels at once, which is still a bunch of eventually 16s, yeah? So that's perfect for us. And so now what we want to do is we want to loop again. We're going to subtract from num pixels every time we process pixels, but we are only going to process 8 pixels at a time, all right? So the first thing that needs to change is this LD3. We're not going to read into the 16-bit pieces. We're only going to chunk it up into the right halves, so it's only 8b.8b. Work on 8 bytes at a time for the red, green, and blue, or in our case, blue, green, and red, right? So 8 instead of 16. 8. Okay, so that's the first thing. So we're going to read a chunk of pixels only into the right half of the V registers. So we're only using 64 bits right now. Because, the reason we're doing that, right? Because doing it with full V registers is more complicated. Because you still have to worry about overflow. This is the easiest way to do it, okay? And then remember that .8b means read into the right half of each register. So we're only filling it up halfway, and that's good for us because we want to make it bigger. We want to widen our stuff, elongate, L for elongate our registers into a different register, okay? So that's the goal there. So then we process them in the way that we need to, and then we'll write them back. Let's pretend that they're there again. We'll do a store. And remember, it's got to be 8b all over again. So instead of here, substitute 16 for 8 everywhere, please. There. That should work. And so really, again, right, we're really only writing the right halves of V0, V1, and V2. So we'll get the right answers in there again, but that's how that needs to work. The process them part is the hard part. And then because we're working on just 8 pixels at a time, we're doing the right halves, right? The right halves of these guys are all 64 bits, right? Which is 8 bytes. So we're processing 24 bytes total every time. And the next address we want to deal with is 24 bytes from now. So we're going to do plus 24. And once we're done with one iteration of our loop, we just processed 8 pixels. We're only working on 8 at a time because of overflow issues. All right. So now I think all that we need to change is this part, add to process them. So that's the hard part. All right. So let's break it down. What we need to do, what we want to do, right, is add up R, G, and B, essentially calculating like an average value, but we'll forget the divide by 3 because that's hard to do. So we want to add up the red, the green, and the blue because whatever number we get, if it's a big number, that means the pixel is very bright and it should have been converted to white. Otherwise, if it was a pretty small number, the sum, that means that the pixel was pretty close to black, closer to black than to white, and so we'll convert it to that later. Okay, so what I need to do is get the sums of these guys, and in order to get a sum and not have it overflow, I need to extend, right? Extend our register from 8 bytes, right, into 8 half words. So you see that our target register, whatever we choose it to be, is going to be using the full V register, whatever one we choose. Whereas this is only using half of it. This will use the full one because I'm taking all these 8 pieces and making them double the size, which is now going to fill 128 bits. All right, so that's what we'll do. All right, so it's UXTL. UXTL is going to be, well, first of all, I got my pixels, and green is in V0, or sorry, blue is in V0, green is in V1, red is in V2. All right, so let's figure out what that needs to be. So I want to extend blue first. Blue, then green, then red. So that's going to be UXTL. It's U for unsigned. We're working with unsigned ints right now. Extend and elongate from V0.8b into let's do V3.8h, right? 8 half words. So now it's twice the size, right? So that's pretty nice. So remember that we're working with just the right half of V0 becomes all of V3 because we've doubled everything. Okay, so that's the goal. And we're going to do the same thing for V1 and for V2. Let's bring them into V4 and V5. Right? So the green's going in V4, double the size, and red's going into V5, double its size. All right. So that's perfect. Now we can't overflow. Now we'll use V3, V4, and V5, and we cannot overflow. All right. So let's add up those values with now just an add on 8 eaches now though. 8 chunks of pixels, but now they're 16 bits long each. That's perfect. So what I want to do is add. Let's just add them all into V3. Add into V3, which is chunked up by 8 half words, 8 16-bit things. I want to add in what we got there already to, like, that was the blue, let's add in the green. V4.8H, and then we'll do the same with the V5. So now I've got the sum sitting in V3, all right? So now V3 is equal to the red plus the green plus the blue. And now if it was we got a like condition based on what we see here. If this was large, we'll make a white pixel. If it was small, we'll make a black pixel, or doing like a threshold kind of operation, okay? That's what's going on. So in order to make that happen, I want to threshold and compare against the value, like the mid-range, right? 120 is like halfway between 0 and 255. So 384 is a good value to compare my R plus G plus B to. So I want to get this number in every chunk of a V register. All right, so I'll do move I into each 8 half-word thing, 128. Okay. So let's put that in. Let's use V4. We got room in V4. Let's put 384 into V4, and we'll copy it, right? Copied into every 16-bit chunk, and that's H, right? H for half word. Half of 32 is 16. All right, so move I into V4.8H, 384, right? Did I say something wrong? Sorry. So it's not this 384, right? But sadly, we can't do that, all right? And we'll just use like a num kind of thing there. But I think I need to explain a little bit further here. So there's an issue. I can't just say 384, right? Let's get this all in one line by itself. This is hard to do. Give me a second. Let's replace that with that. Okay. With something like this. That's kind of what we would like to do, but we can't do it because 384, again, this instruction needs to be encoded in 32 bits because that's how long every ARM instruction is. 384 is way too big. Like it's an immediate value that's just too big to go here. But I know that 384 is 128 3 times. I can move 128 into a V register. All right. So here's kind of what I'll do. I'll do like this. I'll move not 384 because that's impossible. It's too big. I will start out V4 with a bunch of zeros, 8 zeros, 16-bit zeros, and I'll do in V5. I'll put 128. And now do you see, if I just keep on adding V5 3 times into V4, then it will hold 384, right? That's one way to do this. V4 8H, add into itself V5.8H. So now I got a bunch of 128s in V4, 256, 384. Okay, that's the idea. So now it's, yeah, just got to do it 3 times. And so now, finally, now every chunk of V4 holds 384. So that was a weird quirk of like how you can encode immediance in an instruction. You couldn't just do 384 immediately. Okay, you can do 128 immediately, so we use that to our advantage there. And so now I've got all my pixels. I got my summed pixels in V3, and I've got 384 8 times in V4, and I want to compare each chunk against the value there. So each chunk against 384 a bunch of times. That's why I duplicated it. All right. So now I'm going to do CMG. So compare multiple greater than or equal to. I think that's what it stands for. CMGE. I want to compare V3 with V4, all the pieces. V3 8H with V4 8H, and it's going to write back things. This could be lowercase. I'll just use capitals all over the place. And it's going to write the answer to somewhere. All right. Where do I want this answer written back to? Let's do V0. All right, V0 8H. And this is really weird. What we're doing is we're compare R plus G plus B with the threshold value. And if it's true, like, right, if the first chunk of V3 was greater than or equal to, was in fact greater than or equal to the first chunk of V4, then the first chunk of V0 is going to get set to all ones. All right, that's really weird. It's going to set the bits all to ones. And it's going to do the same for the second chunks, the third chunks. It's a little weird. All zeros if it's false, all ones if it's true. And so now I have either a bunch of all ones or all zeros in each 16-bit chunk of V0. Okay, that's very odd to think about, but that's what's going on right now. I have this going on with my CMGE, kind of like this at least. And so now I've got a bunch of I've got a bunch of 16-bit values that need to eventually become pixel values. Either they should be like all ones for 255, right, for white, or 0 for black. And so I'm going to narrow back down, extend reverse, kind of narrow back down my 16 bits into 8 bits. So I'm going to do the opposite of this UXTL. It's XTN. And for narrow it back down, take my 16-bit things, make them 8-bit things, single bytes. And that will convert these values that I have here, which will eventually become red, green, and blue values, into what I need them to be. Okay, so now I want to shrink V0 down into 8 bits again. So it's the opposite of this UXTL stuff. We're not going from B's to H's anymore, we're going from H's to B's. Alright? So it's XTN. We're going from V0, 8 16-bit things, into V3. Alright? V3, a bunch of byte things, 8 bytes only. Okay? So that's the answer. So we just shrunk V0 down into the right half of V3. Alright, that's what just happened. Everything's small again. If it was a bunch of ones, 16-bit ones, it became 8 bits of 1. If it was 16 bits of 0, it became 8 bits of 0, which is exactly what I want, right? Because that's going to give me my 255 or my 0. Isn't that nice? That's white and black if I just duplicate that, alright? So whatever this answer was, sitting in V3 right now, I want to store it back as the red, green, and blue channels, because either it's all ones in each chunk or all zeros in each chunk, and that corresponds to black or white. Alright, that is the answer. That's the answer. So I just need to, if I want to use this instruction, I could have just said V3 a bunch of times, but I'll do it like this. I'll say move into V0.8b from V3 8b. Just want to duplicate it a bunch of times. Alright, do that in V1 and V2. So, actually, let's comment this out before I say this. So now the right half of V0 holds, this is going to be my blue values. This is the blue values I want it to be. We're just duplicating a bunch of times. And then right half of V1 holds green, and then red, and that is V2. Alright, so this was kind of unnecessary, but now I can use this original store 3 instruction, replacing everything back. I've just duplicated a bunch of times. It was all ones or all zeros, and now it's going to be white or black. And that's how that's going to work. I think that's as much as I can say. It is a bit complicated. It was definitely a bit complicated what we just did. There's a lot of moving parts. Your lab, when I force you to do this kind of things, it's going to be easier. It's closer to this example than this one. But this is a very good example of a bunch of different vector instructions that are very cool. And we're going to get a very nice result here. It's going to look very fancy. Okay, so there's my bw.s file. So here's my processing step. Extend, get the sum, get 384 in a bunch of chunks so I can compare against it. And that's going to set ones or zeros, shrink it back down, and like duplicate that. Those are my pixels now. It's either all whites or all blacks. And so if I make this, no, sorry, I need to get in the right folder again. CD for lecture 18. So if I make this, in theory it compiles good. And then if I say /filter, now I can say filter on BW. And yeah, let's do BW on Lonzo again. Lonzo.bmp original. and we will output as lonzo.bw.bmp. All right, and that'll be the goal. And I do have other image files for you. Hit enter and it should work. It takes a little while. Hopefully we didn't mess up, because we're doing more stuff. It kind of feels like it's stuck in an infinite loop right now. Did I mess up? I very well could have. But it looks like we're subtracting, so we should eventually get down to zero land. Yeah, there was a lot more work to do this time though, so maybe that's why. Let's see here. Comparing W1 to 0 seems to be doing the right thing. But yeah, I do think we're stuck right now, so I'll have to figure out what I did wrong. Hopefully it's not messing too much up right now. But yeah, I think I messed something up if it took that long. We're not looping properly. W1 is getting messed up in a weird way, maybe. Yeah, so I will pause the recording right now and see if I can fix it. Alright, we're back now. I legitimately don't know what the problem was, because I just ran it again and hit enter and it's just immediately ended. It's happy this time. I don't know what I did. So I must have just like not typed enter properly. Maybe I typed like shift enter or something weird. But there it is. There's new Lonzo. Let's see if I messed up. So let me add in everything again. You remember what the original Lonzo looked like. Moment of truth. We've got now, in addition to swap the colors, black and white Lonzo. So here's original. And if we did it right, we should see like the light colors converted to white, and then the darker colors converted to pure black. And yes, we do. So the thresholding, I mean, you can pick what your cutoff is. We picked our cutoff of 384. Maybe that wasn't good enough for this image. It was too exposed or something. But that's one way to convert each pixel into just white or just black. Isn't that fun? So yeah, that was enjoyable. There's a lot to explain though, especially for this one, but it's a great example. Please study this. Please ask me questions about this example until you get it, because this is going to help you so much on your future labs and or tests. Alright, so I think that's all that I wanted to say for the lecture part today. I have more to record for different pieces, but that's the main lecture, so I'll stop the video now and see you in the next one.